uh, the small signal gain. We looked at the benefits. What are the possible benefits? We concluded that there is no benefit in terms of gain, output impedance, input swing, output swing. There is no benefit. So I asked you to look at what is the benefit. I think by now you should have the answer. You must have read it. So what is the benefit here for this particular amplifier? Anybody checked it? Like, did you read it somewhere?
Increased bandwidth because of less capacitance between input and output.
It increases what?
So the bandwidth.
Yeah. So why the bandwidth is increased?
So Miller effect is removed. There is less capacitance between the input and the output.
And why that the less capacitance coming into picture? What is the reason for less capacitance? Yeah. So you already have the answer. So I need to know why there is less capacitance. You have read it, right? So and Miller effect has been taught. So Cascode amplifier, you said that BJT version at least has been covered. So you should know this answer, right? So what is the why the capacitance is low? Quickly, these things we need to speed up because these things should have been covered in the class also. So BJT version, although it has been covered, but the concept is same. So what is the why the capacitance is low or why the Miller effect is lesser? What is the reason? I'm not getting any answer. Are you able to hear me? Anybody?
So you're audible. So we did not cover like anything apart from like a very general introduction. Like we just know this is
Okay,
called
so fine. So let us cover it. What can be done? So you have the gate. We are looking at. So first of all, to get that answer, we need to understand the scenario here. That if you are having a MOSFET like this and you're looking into the source, what is the impedance R in, or let me call it small r in, because we are talking about small signal input impedance. So in this case, what is R in? In case you have a structure like this, I mean circuit like this where the gate and drain both are at DC potential. The gate is at some DC potential VG, drain is VDD or whatever, some DC potential, fixed potential. And then I ask you to look into the source and find out what is the small signal impedance, what is the value.
So it's going to be 1 by GM.
Yeah, this is 1 by GM because we know that the gate potential is fixed DC value, drain is also fixed DC value. So, and you're changing the source potential, directly you are applying a VGS. And if you are applying a VGS, the resulting current will be GM VGS. And therefore, the impedance is delta I in by delta V in, which is going to be 1 upon GM. So, if you apply a V in over here, the small signal current change is GM V in magnitude, and therefore your R in will be, this is the current, and therefore voltage by current 1 upon GM. These things you should have at your fingertips. I don't need to remind you. In upcoming whatever topics we discuss, whatever examples we discuss, these things, even other example that we took last time, I think where you have a RS over here and you're talking about impedance looking into the drain of the MOSFET. This you should know the formula. You should understand why it is happening. Not only the formula, but why intrinsic gain GM RO times RS comes into picture, looking into the impedance. Conceptually, also I tried to explain that, okay, why this amplification is coming, why this GM RO factor is coming, looking into the drain. So these things you should remember. Another equally important result is this one. So these are things which, analog designers, IC designers, they should know, they should remember, they should have it at their fingertips. So for this one also, we have a scenario where you have impedance connected at the drain, and now we are looking at the source of the MOSFET, and we want to find out Rin. So as compared to this case, we have added an RD in the drain. So in that case, what is going to be the scenario, and how do we calculate the small signal impedance? So again, the idea is that, see, ultimately when you make a circuit like this, in any circuit, this will not be a floating node. Ultimately, you will have some arrangement over here. Either you will have a RS over here, or you will put a current source over here. Do something. It will be having some condition. But what I'm looking at it, forget about whatever is there below. I just want to find out what is the impedance looking into the source. So it can be in the on the lower side, it can be any circuit, it can be any condition, it can be a current mirror, it can be a RS. So I'm not concerned about that. First, I want to know what is uh, the impedance looking into the source. Like in this previous circuit that we're looking at, the cascode, what is the condition? If I here I'm just looking into, I'm trying to find out the impedance looking into the source of this MOSFET M2. So lower side we have this common source input device connected, M1 is connected, but for the time being I'm just looking into the source of M2 and trying to find out what is the impedance looking into the source of M2. So let's see, what can be said. So let us remove other things. And once again, in order to find out the input impedance, we will put a voltage source, say test voltage VT, and we need to find out what is the IT. And once again, if I ignore the channel length modulation, that there is no lambda, there is no channel length modulation. In that case, because VG, the gate voltage is at AC ground, this is a DC potential, the whatever VT you apply, it will appear as VGS, and therefore the current will simply be equal to GM-VGS. So if you ignore channel length modulation, once again, this result will give you input impedance equal to 1 upon GM, which is not quite correct. So in this case, why easily we are able to ignore channel length modulation? Because you are changing the VGS, like when the drain is at fixed potential and you're changing the source by small amount, the change in VGS and VDS is same, right? So the value of change in VGS, small signal change in VGS and VDS in this case is same. And we know that the change in VGS has a much more pronounced effect on the current. Therefore, in this scenario where the drain voltage is constant, gate voltage is constant, and you are changing the VGS, VDS almost by same amount when you are applying a small signal AC at the source. Gate is fixed DC potential VG and AC signal applied at the source. Therefore, the GM VGS effect is going to be much stronger than the VDS lambda VDS effect. So we can ignore. But in this case, the drain is not at a constant potential. We have a RD at the drain, and therefore, if you try to increase the source voltage, for example, and basically that is leading to a reduction in the current, right? If you increase the VT, it will lead to reduction in current, and if it leads to reduction in current, the voltage over here, it is also going to change. The drain voltage is also going to change. By what factor? Whatever delta I change is happening times RD. So there will be a change in the output voltage or the drain voltage over here by the factor delta I into RD. And if this RD is large, the VDS change can be pretty large. If I assume that this RD is large, in that case, the delta I times RD will create a large VDS change, which may be much smaller, much bigger than the VT, right? So if I assume that the change in the small signal current produces GM VT, the magnitude, because if you're increasing the VT, the current, what will happen? VS is increasing, and as a result, VGS is basically becoming negative. So the current will reduce. So GMVT will be the reduction in current, and corresponding to that, the output voltage will go up by RD. And therefore, if you look at the VDS, so we are getting almost VDS is equal to GMVT-RD. If I assume that GMRD is much larger than 1, then the overall VDS is approximately, VDS change is approximately equal to GM into RD into VT. So this small signal gate to source voltage resulting in large gate to drain voltage. So in this case, I can't easily ignore the channel length modulation. If I ignore the channel length modulation for large RD, it will not give me accurate result because a small change in VGS is producing a large change in VDS. So that conceptually should tell you why ignoring lambda in this scenario is not going to be a good strategy. Is that clear? First, you need to understand what we are doing, why we are doing, and what is the rationale of ignoring some parameter in certain cases, and why in other cases we are not ignoring it. So in this case, why we are ignoring, why we cannot ignore lambda for the small signal analysis in this case, while here we have ignored it earlier. Is that clear?
Yes, sir.
These things have to be very, very clear. So if you don't appreciate these things, try to think about it. Ask me again. If you just ignore it, later concepts will become even more difficult to understand. These are building blocks. These are fundamental, concepts. If you miss it, if you don't try to understand it, don't try to put your head into it, later concepts you will, not appreciate, and things will go over the head. So. Fine. So we have now, we can look at the uh, exact small signal analysis, including RO, and just like we did yesterday, you can find out what is the input impedance looking into the source terminal. So in order to do that, let us draw the small signal model. Gate voltage is again at AC ground. So I put it at AC ground. VB is a DC voltage. And then you have GM, VGS. And you're applying the source voltage. Basically, the test voltage VT is applied at the source, and you have the RO. RO will appear between drain and source, always RO. And there is a RD, which is between drain and VDD, which is also AC ground. So this will also appear between RO and VDD. This is your RD. So this is a small signal model. All of you should be comfortably able to draw this. Any given condition, if you want to analyze the small signal model, you should be able to draw this. Now, we can do the analysis and find out what is the IT. Right? All we need to find out is IT, and therefore we can see that okay, whatever IT is going into this, because this is single path, so this to combine together, whatever IT is going into this, it should exit out of this, right? So these two are parallel paths, RO and GM-VGS, sitting between this drain node and the source node. Whatever small signal current goes into it comes out of it. And conceptually, also you should understand what is meant by small signal. So conceptually, if you are increasing VT, VGS of this NMOS reducer, that means it's going to have a reduction in the small signal, sorry, a reduction in the net current. So if I talk about the direction of the small signal current, it is positive in upward direction. That means into the source, right? But for the MOSFET, actually the current is reducing, because for the MOSFET, the positive current is ID, which is flowing from drain to source. But the small signal input current is positive in this direction, because VT is increasing. We are trying to basically reduce the VGS, and that is going to basically lead to reduction. So the net current, the MOSFET will basically be ID minus this IT mod. So just to avoid confusion, if I say that I'm talking about the absolute value of the small signal model, the MOSFET current is going to reduce by ID minus mod IT. IT is anyway positive. So now figuring out, okay, what is the expression? So again, simple, we can find out what is the net current. So GM VGS, GM VGS, VG is 0 and VS is VT, and plus you have output. Output is nothing else but IT times RD, right? Whatever IT flows into the RD, you get IT times RD. So IT times RD. So this is your output voltage VD. So IT times RD minus VT, right? Because this is the this is the current flowing into this path. So divided by RO, which is now the current. This current is ITRD is this voltage minus VT upon RO is the current flowing in this direction, and GMVTS is also current flowing in this direction. So this should be equal to minus IP, right? So this, if you look at the direction, GMVGS current plus this VD, which is written as ITRD minus VT upon RO. This should be equal to minus IT. This should equate. So then I can find out what is the net current. So GM, we are getting VT plus we are getting 1 upon RO. This is equal to, of course, with a minus sign, and I can take IT over this side. So I'm getting basically 1 upon RO, 1 minus sign 1, and here I will get 1 upon RO times basically RD is also coming to picture, RD. So this is what you are getting. Now I can find out what is my sorry, what did I? So VT is basically I have to take the VT out. So in this side it is minus VT times GM plus 1 upon RO. So I can take the VT by IT, which is the impedance we are looking for, which is 1 plus RD upon RO divided by GM plus 1 upon RO. And then I can resolve it a little bit, RO plus RD upon 1 plus GM RO. Now, in this factor, generally we know that this GMRO is the intrinsic gain of the MOSFET, which is again a large quantity. I can ignore the 1, and this is going to lead to what? This is approximately equal to RO upon 1 GMRO. So this will be just around 1 upon GM plus RD upon GMRO. RD upon GMRO. So this is the net impedance we are getting. So as we have discussed that conceptually, what did we see? Conceptually, we saw that this expression 1 upon GM that we get when you have RD equal to 0, right? So when RD equal to 0, anyway, the impedance is 1 upon GM as expected, right? So if you put RD equal to 0, the condition is like this. The drain resistance is 0, and therefore the input impedance looking into the source should be simply 1 upon GM. So this is correct. Now, if your RD is large, what we said is that if your RD is large, you cannot ignore the RO. So if your RD is large, you have to take into account the second quantity also, second term also. And here what we're seeing is same, we have the RD getting divided by the intrinsic gain of the MOSFET. So whatever resistance is in the drain of the MOSFET, or whatever resistance is connected between the drain and the AC ground of the MOSFET, looking into the source of the MOSFET, that gets divided by the intrinsic gain of the MOSFET. In this case, remember the situation was that whatever resistance is seen in the source of the MOSFET, or connected between the source and AC ground. So here you have a RS connected between the source and the AC ground. When we look into the drain of the MOSFET, that impedance gets multiplied by the intrinsic gain. You are getting multiplied by the intrinsic gain, and we have discussed the phenomena what is happening. Here it is just opposite. Whatever impedance you are seeing, whatever impedance connected in the drain between the drain and the AC ground of the MOSFET, looking into the source, that gets divided by the intrinsic gain. So if I assume that the RD is uh, if I assume that your RD upon RO, right? So here, if I take 1 upon GM common, I am left with 1 plus RD upon RO. So in case I say that, okay, RD is much greater than RO, then only I can ignore 1 and I can get uh, the RD upon RO. So in case you are having RD upon RO much greater than 1, suppose RD is much larger than RO. So in that case, I can ignore the first term, and this will simplify to RD upon GMR. And again, why it is happening conceptually also, why this expression is coming in this scenario, that also we can see. So for that, it will be easier to visualize if we rather use a current source. Suppose if you use a current source IT, right? The gate is at DC potential, whatever VB, and then you are applying a test current IT, and you're trying to see what is the impedance looking into this. So if I have, say, the input current, the small signal current that you're providing is IT. Now, whatever IT goes inside, right? Whatever IT goes inside, what should be the small signal current in the drain? Like what should be the current coming here? Because this is a series element, right? So even if you include the RO of the MOSFET, ultimately this is source to drain. Source to drain, whatever it has to be same, right? IT. So this is also going to be IT, and therefore whatever input. So this you should very carefully notice that whatever input current you can enter into the source, the same should come out of the drain, right? Unless the body bias splitting problem and all. So for the time being, assume that body terminal is not taking any current away from the channel. Whatever current is entering into the source, the same current is entering into the exiting from the drain. So now if I see this, then the voltage produced at this point is simply, because this is AC ground, in terms of AC, this is ground. This is also ground in terms of AC. So the output voltage is simply IT into RD. This is your output voltage. And then this is if I look at the overall uh, gain. So if I find out what is Vs, so this is AC ground anyway, 0. And here we have Vs. So what is Vs required to produce an output gain of basically output signal of this one? So this is like a common gate amplifier. So you are having VGS. I want to find out what is the delta VGS required to produce a output gain of ITRD. So if I do that, then it is basically uh, it is going to be ITRD upon basically GM. So the VGS is something like this, and so the delta VGS produced because of the applied current, we can say that okay, it is going to be ITRD upon GM, and then you can say that if you talk about the uh, or suppose we look at the IT. So here, if I'm looking at say VGS, delta VGS, in this case, if I approximate that, in this case itself, if you see the applied VT is resulting in IT, and then we are having a VDS is equal to GM RD times VT, and that is basically much higher than your. If I assume that the GMRD is much greater than 1, that is much higher than the applied VT, and therefore, if I talk about the IT, so in this case, it is just a minute. So this one, if I see the so effectively what is happening is you are having delta
Sure.
VGS, which is much smaller than the output signal swing produced, and that overall gain will be determined by RD if your RD is much greater than RO. So if I assume that the scenario that we have taken here, that is RD being much larger than RO, in that case the overall output voltage itself will be or overall small signal gain from the input to the output, that will be determined by uh, GM times RD. So in that case, I have the delta VGS, which is IT RD divided by the gain. Just a minute. So there was a nice explanation I had thought of. You can conceptually look at conceptually without equations, you can arrive at this. So this one, of course, tells you the reason that why it is happening. But conceptually, I'm just trying to arrive at this expression without derivation. So that uh, from this part anyway, it is clear, right? So what is happening? So why RO is playing an important role and why you are getting uh, effectively a smaller basically impedance. So here, if you had directly RD connected, then of course the impedance would be just RD. So if you are applying VT directly to RD, in this case the impedance is simply RD because the current will change according to RD. But now you have inserted this MOSFET in series and you are applying the voltage at the source of the MOSFET. And what we are seeing is the overall impedance has been reduced. So as compared to applying the test voltage directly to RD, if I'm applying the test voltage to the source of this MOSFET, what I'm saying is the impedance is getting reduced to RD upon GMRO. And that basically means that if the impedance is getting reduced, what does that mean? That for a given VT, my IT should increase, or basically the amount of IT that is going, that should increase. And that is happening because here you are basically applying the same, you are basically applying the same amount of voltage change to the VGS of the MOSFET, and that is going to result in GM times VT small signal current. And that small signal current uh, is going to get basically multiplied by the, if I talk about the intrinsic gain, it is going to get multiplied by GMRO in case RO is significantly basically lower than RD. In that case, the intrinsic gain becomes almost equal to this. And as a result, you are seeing a larger voltage drop across RD as compared to the original case. and therefore the resulting current is also larger. So what is this doing is basically for a given applied voltage, it is enhancing the voltage drop across the RD because of the MOSFET's action. If you had if you had only connected VT, the applied voltage across RD is simply VT. But now, because of this VT applied to the source of the MOSFET, it is producing this VGS, and because of that, there is a small signal current produced. And assume the scenario for simplicity. So assume the scenario that your intrinsic gain, in this case, currently from source to drain, the intrinsic gain overall is dominated by GM VT times RO. And as a result of this transistor action, the drain voltage is uh, going up, or basically there is a large change in the drain voltage. And therefore, for a smaller applied voltage, the effective voltage drop across RD, that is increasing by a large factor given by GMRO. So that basically conceptually tells you that even without solving why for a given RD, the impedance looking into the source is getting reduced by this factor of GMRO approximately. Is that clear?
So,
Yes. Hello. Yes.
Yes. So like this one, if you want to derive without small signal, like we can say this way, right? Like if we inject current IT, then voltage at drain is ITRT. And so the change in gate voltage we require is that divided by the gain, which is GMRO parallel RT. So then the input resistance comes out as the same, RO plus RT by GMRO. That can be the reason.
Yeah, so the same thing that is, so if you are saying that this is ITRD is the voltage gain and divided by GMRO. So if you say GMRO parallel RD,
then we'll get the
yeah.
first
So,
formula.
yeah, so the same, so the same concept basically. So this is same thing as this one that I'm saying. If you are applying a so here also, if you look at the gain from this point to this point, exactly, if you see, this is not the exact expression, but yeah, approximately you can say that, okay, this is the overall gain. And effectively what is happening is, as compared to the applied voltage VT, you are getting a much larger voltage change across the RD, and therefore the amount of current that is flowing, the small signal current or the change in current in RD, that is also much larger by the same factor. So both ways, the voltage mode also you can look at it, or the current mode also you can look at it. So it like conceptually, this is what is happening. And in other case also, we had seen why conceptually the impedance is getting a big boost. So both ways, we need to remember this configuration, that if you are putting a RD in the drain, looking into the source of the MOSFET, that RD gets divided by GMRO. And opposite side, if you're putting RS in the source and then looking into the drain side, the impedance gets boosted by basically GMRO, intrinsic gain. So this is clear?
Yes, sir.
Yes. Okay. So now, if this is clear, now we can basically understand in the previous case, whatever we started with, for example, this one. Here, now we can probably look at what is the impedance or what is the gain from the gate of the M1 to the drain of the M1. That is what we are looking at. If you want to find out Miller effect, all we need to do is find out the gain from the gate of M1 to the drain of M1, because the Miller capacitance between the CGD between the gate of M1, drain of M1 will ultimately depend upon the gain between the gate and the drain of M1. So in order to do that, we can now if we assume that this RD is much less than RO, so this equation, what does it tell us? So if we have already conceptually discussed, if the RD is much lower than RO, then it is simply 1 upon GM. RD approaches 0, we know that the impedance looking into the source is 1 upon GM. So since the overall impedance is 1 upon GM plus RD upon GM RO, if RD is much smaller than RO, we can simply ignore. So it will be 1 upon GM. Assuming that is the condition, what will be the gain from gate of M1 to drain of M1? A1 is, I am calling a VD1 upon VG1. What is this?
Minus GM1 by GM2.
Minus GM1 into, so this is like a common, if I look at it, if I am taking, suppose imagine this is a common source amplifier, I'm taking my output here at the drain of M1. So in that case, impedance looking upward is simply 1 upon GM2 because we are assuming the condition that RD is much lower than RO. Under that condition, it is GM upon 1 upon GM2. And if we assume that here the currents are same and W by L are similar, this is close to unity. So as compared to common drain, the normal common source where you are directly connecting RD over there, gain was GMRD, which was a large number. Here it is close to 1. Therefore, the Miller effect is reduced. So as compared to 1 plus GMRD, you are getting 1 plus 1. So definitely that number is much smaller. Therefore, the multiplication for CGD does not happen, and the effective capacitance that you get over here is smaller as compared to the common source amplifier case. So that is responsible for basically enhancing the bandwidth, right? So that basically reduces the capacitance and basically shifts the high frequency pole at the input node, that is the gate node, towards higher frequency and enhances the bandwidth. Because earlier design, if you see, this could have been the dominant pole because this is giving you a larger capacitance relatively. And if the source impedance is large, then definitely becomes the dominant pole. So now that is the benefit that we are seeing. And so in order to get the gain, we have anyway seen that, okay, the gain point of view, we are almost getting the same GMRD value. And now from the point of view of bandwidth, we can see that, okay, once we understand how to find out the impedance, we understand that what is the benefit in terms of the frequency response. So I hope this part is clear. Any question before we proceed further? So, these two expressions for the impedances part, impedance looking into the drain of the MOSFET and impedance looking into the source of the MOSFET is very important, and you should mug it up and remember the concept behind it, why that factor is coming. Conceptually, you should be able to explain. So that part you should be aware of. Okay, so any other question before we proceed further? So
Sir,
now, yes.
Sir, here you mentioned that the equivalent capacitance at the gate will give us the dominant pole, right? So
Yes,
how,
provided you
sir,
have
but
a driver, the source is having enough resistance.
sir, but if we sum up all the equivalent resistance, then we will get a total of 3 independent capacitances, in which the equivalent capacitance which arises at the drain of the M1, those will have many components, right? Like CDB1, CGS2, CSB2. So it
But that
will
is not
give us
getting Miller multiplication, right? So we are talking about Miller multiplication. So if you talk about the capacitance at this node, so this one you should be able to see even without doing calculation and drawing. So see, Miss, here without even writing down the equation, I should be able to see which are the capacitances coming. And is there any Miller multiplication for this node? At this node, whatever CGS is coming, is it getting Miller multiplied?
Sir,
sir.
the source to body and drain to body, those are junction capacitances, right? They're very low. They won't contribute towards the dominant pole.
Yeah, and what is so CGS of you are saying that this node is having CGS. CGS is also between the source and the body, which is AC ground. So this is also not seeing any Miller multiplication. And these are anyway the body suppose AC ground. So the signal, the capacitance CSV is generally small, the junction capacitance. So it's almost 10 factor of 10. You can see 5 to 10 smaller as compared to CGS of a given MOSFET. So this capacitance is small. You have the TDB of M1, which is also relatively small. CGS is only major component over here, which is also not having any Miller multiplication. This guy was experiencing in the earlier design. This one was experiencing a large Miller multiplication, which is now mitigated. Is that clear?
Yes, sir.
Output node also, if you see what is the situation, you will get CDB of M2, right? So I don't need to write it. You can visualize the CDB of M2 and then CGD of M2. CGD is also between drain and AC ground, and CDB is also between drain and AC ground. So both of these are small capacitance. CGD is also generally significantly smaller fraction of CGS. You have seen that saturation region. What is the CGS? It was just the overlap capacitance effectively. So CGD is also significantly smaller, maybe a factor of 5 smaller than CGS. CDB is further smaller, maybe a factor of 10 smaller. So these two capacitances at the output node are also low. So in the earlier design, the dominant capacitance, at least that we are sure that it would be at CGS of M1 because of the Miller capacitance, and it will definitely create dominant pole provided the input itself is coming from a relatively, it's coming from a stage which is having sufficient output resistance comparable to RD or basically few kilo ohms of impedance. Then this will become dominant. Is that clear?
Yes, sir.
So those things I'm not doing that. Okay, find out the expression for CG, total capacitance at this node and this node. Those things visually you should be able to see and decide which one will be dominant. So now other things are like okay, if you want to do swing analysis and frequency response, it is clear that okay, it's benefiting. If you want to do say input output swing, we have anyway seen yesterday in detail. Input swing likewise you can figure out. I will not go into it right now. So let us look at the case where another thing that you may notice is, so if you look at noise analysis, for example, noise analysis also we can take one note. So because if you are looking at say suppose I transfer the channel noise, I represent it as a gate noise voltage of this MOSFET. Likewise, here also I'm capturing the net noise of this transistor as the gate voltage. I can transform, right? The channel current can be divided by GM square and we can get it to the gate. In this case, this is your VNG1 square and this is your VNG2 square, which is both having 1 upon F component as well as the thermal component. So I have divided the channel current because of thermal noise divided by GM square will give you VNG1 square, likewise VNG2 square. And here the input transistor, the first transistor M1, is definitely having similar effects. So whatever we have studied for the common source, almost similar effect because this gate voltage will result in a small signal current and it will get transferred into the output voltage. So similar behavior. So whatever small signal current is produced by this gate voltage noise, it comes at the output and that basically reflects as the output signal noise. So there is no change. However, this one, if you talk about the VNG2 square, so we know that this is like if I want to find out the gain from here to here, again, this is like a source degeneration, right? So this is like a common source amplifier with source degeneration. So I can ignore, basically I can replace the M1 by RO1 and then try to find out what is the effect of this noise voltage VNG2 square on the output. So again, we have seen that the moment you have this RO, especially the RS here is pretty large, right? So RO1, in this case, it may be even larger than RD, right? So in that case, the overall gain from this point to the output will be pretty small. And therefore, in the analysis, people may ignore the effect of this M2. Okay, means this because of this cascoding and this source degeneration, this cascode device compared to the input device will have very small effect, and therefore we can ignore it. So that is also you should take note of. RD will have its effect just like the previous case. So whatever was the situation of RD, that remains almost the same. Only role is you need to take note of this M2 situation. This is clear. So if you have to find out the net expression for the output voltage noise because of all these transistors, so it will behave almost like a common source amplifier, and the noise of M1 will count. Now noise of RD will count. Noise of M2 will not count, or you can ignore. Is that clear?
Yes, sir.
So GM of the M2, if we take for VNG2 whole square, it's coming 1 by RO2. So like, it's like that's why we can ignore it, right? Like because 1 by RO2 is a very small number.
So overall gain is GM RD upon 1 plus GM RO R1 in this case, right? So GM R1 RO1, if I say that it is the intrinsic, so you have to look at the comparative value. So if I talk about the gain, the noise contribution of the input device, as compared to that, this is negligible. So this one is getting, GM1 R1 or basically GM1 RD, right? Whereas this one is getting GM1 RD upon 1 plus GM RO1. So GM RO1 is a large quantity. So as compared to the noise contribution of this device, we are ignoring the noise contribution of this device. Is that clear? So now let us look at some other, extensions of this one. Uh, Last few days I've been thinking of giving some assignments also. I have not given some assignments, but today I will try to give some assignments so that you can carry out. So based on whatever we cover today. So let me. So you have been taught the common collector, right? Common collector has been covered in your class, and also I think what else? Your common collector has been covered.
Yeah, source follower, emitter follower.
Okay, and common gate and common base has also been covered. Common gate, common base.
Yes, we had done the just small signal gain R in and R out for those. Frequency response we had not done for these.
Okay, so fine. So let us first look at the modification of this cascode. So now if we look at the load, so one thing is that okay, the common source amplifier definitely as compared to common source amplifier, we are getting a better bandwidth. So that is one advantage of this particular configuration. And it can be used in differential versions also wherever there is a need for enhancing bandwidth. So that we have to be careful about. Now, if we want to, rather than bandwidth, if our priority is to get gain, so we want to get better gain. So if I apply active load, current source load, in that case, how does it change? So this is VB still, some constant VB2 gate voltage, and this is also call it a why do I call it B? So B generally stands for bias. So just to avoid confusion, I'm writing it VG, VG2. And this one is VG3, also constant bias. This is VD. And then I have to take the output over here, V out, and then I have V in over here. And now I want to find out what is the small signal gain from input to output. So again, the concept remains same because whatever GM V in you apply, the same small signal current is produced over here. It will come here, and then it will get multiplied by the output impedance, which is RO3, right? So RO3. So this is the output gain, and therefore my overall gain over here is GM RO3, right? Input output gain GM RO3. And if you look at the impedance now, if you look at this particular point, what is the impedance looking up? R up at this node, R up at drain of M1. What is that? So we have seen that looking into the source of the MOSFET with an impedance RD. What is RD in this case? It is RO3,
So far now.
right? So it will be RO3 upon GM2 RO2. Whatever is the impedance looking into the drain of the MOSFET, that is RO3, and that gets multiplied or sorry divided by the intrinsic gain of this MOSFET, which is GM2 RO2 plus 1 upon GM2. If I assume that RO2, RO3 are similar, then basically now it is going to be 2 upon GM. So there's a minor change. Earlier it was, if I had RD and if I had assumed that RD is much less than RO, then it was 1 upon GM. Now only thing is it has become almost 2 upon GM. Still the gain from here to here is small only because, earlier if I can assume that GM1, GM2 were similar, now in the earlier case you were getting a -1 gain, now you will get a -2 gain. So still, Miller effect is getting mitigated. Still okay. Is that clear?
Yes, sir.
And the gain is GM RO3. So you are getting a good gain GM RO3. If you did not have this, it did not have this particular Cascode device. If you had only the M3, what was the gain? If you did not have M2, what would be the gain?
GM into R01 parallel R02.
RO3 parallel RO1. Yeah.
Yeah, so in that case, it will be GM RO1 parallel RO3, and that is because in this case, the R up, whatever you are getting, it is going to be RO3. R down is at this node. In that case, it would have been just RO1. Both are comparable. So you need to take into account RO1 parallel RO3. in this case, if you talk about the small signal current produced by this channel, at this point, R up is RO, and the R down, however, is much larger, right? GM RO times RO or GM RO square. So I can ignore that, and therefore here we simply write GM RO3. Whereas in the earlier case, it was GM RO1 parallel RO3. If I assume that those are equal, it will be GM1 by 2, sorry, GM RO by 2. In this case, it is GM RO. So gain also gets enhanced because of this. So it's not, that is not a major reason. Major benefit here is that, okay, still Miller effect is getting mitigated. Now,
Sir?
yes.
Sir, in the previous case and in this case, the gain we are getting is negative, right? Like minus,
Yes.
minus 1 or minus 2. Then,
Yes.
then how can we neglect that Miller effect, sir? It will get added. Now, capacitance will be 2 times of CG. Right?
Yes, but it is much less than GMRD, right? GMRO times 1 plus GMRO times CGD. Right now, you are having 2 times CGD.
Oh,
so
okay, okay. Sir.
Number
So you're comparing
is
it.
still much. Okay, so now the question is that you want to increase the gain. Means I am not happy with this gain. I want to improve the gain further. Then what is the approach? So can I stack the load, stack more transistors on the PMOS side so that I have a better impedance looking upward, right? So there again we can look into the small signal model, what is happening. So here I can stack 2 PMOS now. So this is called cascode load. So I am not only having a input side cascode, but I am having a cascode load also. So VG, let me call it M1, M2, M3, and M4. And this is your VG3, VG4. These are all constant bias voltages. This is the input voltage. VG2 is also constant bias voltage. And my output is here. So what I have done is I have replaced the simple current source load by a cascode load. So this is cascode load because I have stacked 2 transistors. So here now, if I talk about say overall small signal gain, what is going to be the small signal gain in this scenario? So in order to find out this, we can first of all we need to find out if we are able to find out that okay, what is the small signal current coming out of this node? Like what is the small signal current provided by this lower branch? Then I can just simply multiply it by the impedance upward. So if I know that I am applying an input signal over here V in, and this lower part, the input part, is responsible for producing some small signal current. So whatever this is your load, whatever RL or ZL. So whatever small signal current is going into the RL, that multiplied by RL will be my gain. Right? So all I need to find out what is RL and what is IL. So if I am able to find out what is IL, what is the small signal current going into the load, and what is RL, I'm done. So RL is already known to us. What is RL?
So
GM3 R03 R04.
Yeah, approximately. So looking into the basically drain. So this is your drain of the PMOS. Looking into the drain of the PMOS where you have a source resistance, right? So this is just like in case of NMOS. Here also you have the same scenario. If this is your M3, you are looking into the drain of the M3, and in this between the source and the AC ground you have RO4, because here looking into the drain of M4, the impedance is RO4. So this is a scenario. We are looking into the drain of M3 where the impedance into the source of M3 is RO4. So from here to here, I hope you are able to correlate. There is no problem. Gate is anyway AC ground. So this is the situation, and therefore the impedance looking into the drain of MOSFET is going to be GM approximately is going to be RO, the GM3 RO3 multiplied by RO4. So intrinsic gain of the MOSFET multiplied by the impedance in the source. This is RO4 approximately. So that's basically in terms of, I would say, if I talk about RO being equal, then it will be GM RO square. So if I just talk about relative value, it is of the order of GM RO square. Fine. So that is a large impedance, right? So as compared to RO, we are getting GM RO times RO. So there's a boost of R. That is good. Now, next is what is the small signal current going up? What is the small signal current going up? Means ultimately we want to find out what is the small signal current coming out of the drain of M2.
So it should be
GM1
GM1 time.
GM1 V in.
GM times V. Okay. So now we also need to see whether this small signal current. So is it going to flow directly into the whatever current you are having GM V in 1. So V in is applied current. Sorry, the signal input gate voltage, and because of that you get GM V in small signal current, which is basically flowing out of this MOSFET M1. But is that all going to go into the source of M2 and going to the drain of M2 mathematically, first of all?
So there'll be current division, like we have RO1 and we have 1 by GM2 at the M2.
Is it 1 upon GM2?
1 upon GM2 up and down is RO1. There'll be a little bit of
Is it
current.
1 upon GM2 looking up at this node? What is R up? If I find out R up at drain of 1, what is it? We are looking into the source of M2 where the drain resistance is what? So this is a scenario. If I look at this, the scenario is this. This is your M2. We are looking into the source of M2 and there is a resistance, small signal resistance between the drain of M2 and ground. What is that? GM-RO square.
GM3RO3.
And therefore now the impedance looking into the source of M2 is approximately going to be what? Exactly, it is 1 upon GM2 plus GM-RO square upon GM2 RO2. And if I assume that all are equal, it is, RO are all equal. So here we are left with 1 upon GM plus RO. Right? This is what we are left with. And this we can ignore GM, right? So 1 upon GM generally is much lower than RO. So basically we are getting RO. So now, RF over here is RO, right? And what is R down? That is also RO. Right? At this particular node, if I now see, what is the story? The story is that here also you are having RO looking, because that is the MOSFET's its own impedance, and looking up also it is RO, right? So here there's a half current division. So whatever small signal current is being produced, you are applying a V in, and that is producing GM V in, and you have the MOSFET's M1 own RO1, but looking upward between this point and AC ground, you also have another RO. So therefore, what current will go into upward RO, right? It will be half. So GM V in by 2. So therefore, now this MOSFET is coming once again in series. So whatever current goes up, the same current will come out of the drain, just like the common, that Casecode example. So here, once we have found out this gain, this current, GM1 V in by 2, the same current exits over there. And once we have that current here, we know the impedance the impedance provided by the upper branch, which is also given over here. And then we can multiply the 2 to get the gain. So basically, GM V in by 2 times GM RO square will be coming at that node. So we get overall gain GM by 2 and GM RO square. So what is the gain? Effectively, it is GM RO square by 2. So as compared to the intrinsic gain of the MOSFET, we are getting square, right? So this is significantly large gain. So this structure, the benefit is that it can give us much larger gain. So square of the intrinsic gain of the MOSFET, which is a good thing if you want to build amplifier where you want to get very large gains, like when you are building amplifiers where you want to get 10 to the power of 5 gain, 10 to the power of 4 gain. We have discussed, right? So the gain requirement depends upon the accuracy and linearity consideration. In op-amp, we have discussed if you want better precision, you want much higher gain amplifier. So here we are seeing that even in a single stage, this kind of amplifier can give you a very large gain. This is clear? Any question?
So here, if we use the other definition, then it is coming still GM1 instead of GM1 by 2. Like if we just short V out to ground and then find GM of the overall circuit.
Short V out to ground.
like capital GM into capital R out. That is like the second method of finding gain instead of using small signal. So like V out we short to ground, and then we apply V in and we measure how much I out we are getting, and then I out by V in is our capital GM.
That method, if you here, if you are just applying, you're shorting it and then finding out. So here you have to take into account the loading effect, right? So because of the load, what is the overall current division? So you can't. So here, if your load is changing the overall small signal current which is flowing into the load, depending upon the load, your small signal current is getting divided. So you need to look into the exact loading condition and then find out what is the gain. So if here. In the exact analysis, we have the small signal current getting reduced because of the larger impedance. It is not basically, it is getting divided because of a large impedance looking to the drain. So here, now you're getting a larger voltage change. Earlier, because the impedance at this node was low, so the voltage change here was low. But now this node itself is going to have significant voltage change. This, of course, it has much larger, but this node is also now having some voltage change and impedance is large, because of which you are getting the current getting divided. So we need to count for the actual load. Yes, any other question?
So in this and the last one, we have to provide a bias for the output, like ourselves. It doesn't do that on its own.
Yes, so bias considerations we have not looked into so far, and for single-ended this kind of amplifiers we don't even use because biasing is difficult. So this is building your concept for the differential amplifier, because in differential amplifier ultimately we will be using this, and there the bias conditions can be met. In this case, biasing, for this kind of amplifier you can't have a easy bias, especially for on-chip circuit. Breadboard circuit you can bias. You can use capacitors and you can do all kinds of things to bias this circuit on your breadboard. But in chip, this kind of output biasing will be very difficult to achieve. Especially here, you have a very high output impedance, right? So even a common simple, load, even simple active load, this one is also difficult to bias. So even this one, forget about this one, is having much higher gain. So it is even more difficult. Even this one is difficult. And the reason, simple reason, conceptually, what do you see? So that lecture, I think one of the lecture I had shown something recording where I had shown the dependency on lambda. There is a, if you find out this V out DC, it is dependent upon all the device parameters, lambda, etc., which can vary a lot. And it is not a very deterministic value. So for a given gate voltage DC over here and VG2 over here, this V out DC is very sensitive to the device parameters. And the gain is also high, right? So the gain high means what? In your transfer characteristics, this curve is also very steep. This is very steep. If this curve is steep, that means if you are trying to bias it over here, right? So you have a very small window basically. And it's very difficult to ensure that automatically by just sizing these devices or fixing the VG1, VG2, you will end up in this narrow range, right? It's very difficult. Therefore, without feedback, we can't do it. So generally we use feedback for biasing this kind of circuit, and that is possible for differential mode. Single-ended it can be done, but it will require some capacitors, etc., which is again not feasible for the single-ended version. So that also should. So one of the ways of biasing this may be that okay, you can, for example, put a big resistor over here, big resistor, and you can. So this resistor is pretty big, so that the DC potential over here gets established because of the V out itself, and then you can put another resistor over here, so that itself establish the, and then you put a big cap over here between this point and VDD. So this is what we used to do in lab. So this RG1, RG2 is very big. Ratios are such that you get a proper VSG for this PMOS, and then you get a DC potential over here will be determined by the voltage division, and that basically helps you in getting the self biasing. But this is not practical for on chip. So this is just for toy experiment you can do. But actual circuits in your mixed signal ICs, this kind of resistor capacitors cannot be used, especially the capacitor, big cap, etc., cannot be used. So this is not a plausible scheme.
So the biasing for the current, we can just do like a current mirror sort of thing, right? We can just put a reference current and get the
Current
voltage.
mirror is not a problem. Output voltage is a problem. Current biasing, you can do whatever you want, but the output voltage will not be stable. You can't ensure that it will be exactly midway. Here also means current biasing you can do all the whatever gate voltage required for these MOSFET, that is you can current mirror you can achieve, but you can't ensure that this will be at the midway, because here the curve is even more steeper.
So and like so if in the example previous class we had put current source as well as diode connected load in parallel at the drain.
Yes.
So like when we use that one, because then the voltage would be defined by the diode connected load.
Yes, but the gain is also ultimately determined by the current division and GM1 upon GM2. So if you put diode connected load, then it's the gain the gain that you're achieving here, that will be gone. So here the target is to get a big gain. So here conceptually at least we can understand why the big gain is coming. But biasing this node in a single-ended circuit is very difficult. We don't use it. Nobody uses this kind of circuits in single-ended. So in differential circuits, when we do differential amplifier, etc., they are ultimately we break it down for analysis purpose. The same analysis will come. There I will not derive it again. So I will tell you that okay, this is a single-ended analysis we have already done. You know how to do the gain. This circuit is giving you this much gain, so that you should figure out. So that is what we are going to look at. So this is while I am discussing this, it is already basically discussion of the differential mode, because in differential mode these things will come. I will just put this load and say, oh, we have done this already, and this is the gain. That's all. Conceptually, we will understand, but will not do all this again derivation. So now, what about the Miller effect in this case? Quickly, Miller effect, quickly. We have to speed up certain things. In this case, what is the situation of Miller effect? Bolo, jaldi. We have to proceed fast. Some of these concepts we have to quickly find out. Yes.
So like here the gain from Vn to the drain is going to be substantial. Like it won't be just 1 by GM, it will be RO. So again we'll have the bandwidth problem, I think.
Okay. Yeah. So we already seen that answer is already written before you. So here we are the impedance at this node is what we have seen, that is RO. Looking down, it is RO of this MOSFET, and looking up, it is RO of the upper MOSFET. And therefore, you are getting overall impedance over here RO by 2. And therefore, now the gain from input to this particular point is GM RO by 2. Therefore, it is no longer small. It is same as simple common source amplifier with active load. So gain is pretty high now. So now you cannot ignore. So there now the Miller effect will be coming into picture. So although the advantage is that you have got huge gain, but bandwidth again got limited because of the Miller effect coming back into the picture. So that you should be aware of. Is that clear?
Yes, sir.
What about the swing? So quickly we need to understand the swing. So definitely looking at this stack, anybody can understand that the swing will now be a limitation. It will definitely be lower. Whether you talk about input swing, output swing, both of them will be lower. So what about the output swing? Now this is VG, and this is your VG2, VG1, VG3, VG4. Quickly. So now what is the output swing over here? Ultimately, we know that it is going to be VG3 maximum voltage. V out max is VG3 plus mod VTP. If I say all the VT are same mod VTP3, but we can assume that all of them are same. So this voltage can go maximum value to what? VG of this one plus VT. Because if this goes higher than that, this MOSFET will be entering into triode region. So the maximum voltage that is allowed at this point will be determined by the VG3. For a PMOS, remember that the drain voltage, if it goes higher as compared to gate voltage, it will enter into triode region. If the drain voltage is higher than VG of MOSFET by mod VT, that means the channel is getting formed. Right? So channel between the channel and the gate, the voltage is greater than mod VT, and therefore triode region starts. So this is the upper voltage. Lower voltage, again for the MOSFET, M2, right? So here if it goes down, which will enter into triode first, this M2, because gate voltage is fixed, drain voltage is going down. So minimum that you can go at the output will be VG minus VT. Sorry, this is NMOS, so you can just write directly VT 2, right? VTN2, whatever VTN2. Yes. So this is clear. Now, in order to maximize this, if you have to maximize, what will you do? Maximizing the swing, output swing means what? I have to increase this thing, right? And I have to reduce this thing, because this is my V out max, and this is my V out min. So in order to maximize the swing, I have to increase the V out max, maximum allowed voltage at the output, and reduce the V out min, minimum allowed voltage at the output. So what will it depend upon? So for example, V out max, for that we have VG3. So how will I reduce, how will I basically increase this? Yes, on what
So
parameter this? Yes.
So it'll depend on VG4. It'll be VG4 plus VT. That will be the maximum you can go.
Yeah, so this voltage ultimately maximum, what is the value you can have, because you are having some drop over here, so VGS drop over here, and if this voltage goes up and you're having some ID, you have some bias current, for that ID this source voltage also has to go up, and then maximum value at this point will be determined by the VG4. So this particular value maximum, what is the value possible? VG4 plus mod VT 4, right? Maximum value at this point is VG4 plus mod VT4. So ultimately, here, if you go on increasing VG3 by same amount, this also goes up, and therefore finally this will enter into triode region. So now the question is, how will you maximize? So what will you do if you suppose the condition is that you need to improve the swing? So what is the strategy? What will you do? What will help you in increasing the swing? I have to minimize this, two things. So I have to minimize once again this drop also, right? So VG4 also, the difference between VDD and VG4, if I can minimize, that means I have to increase VG4 also. If VG4 goes up, this allowed voltage also goes up. If this allowed voltage goes up, then this maximum allowed voltage also goes up. Ultimately, I have to minimize the VSG. How will you minimize the VSG?
So by increasing the width, W by
Increasing the
L
W by
ratio.
L. So for a given ID, if you just increase W by L, the required the required VGS will go down, or in case of PMOS, you can call it VSG will go down, and therefore the upper end will increase, upper limit will increase. Same thing you can talk about the lower one. Lower one also you'd like to minimize VG2. If you minimize VG2, what will happen? This node will also, for a given ID, if you want to maintain ID, you have a this voltage will also go down, VGS will go down, and then this minimum will be determined by VG1 minus VT. So in order to be able to apply minimum possible VG2, you need to minimize VG1 also. So for that, again, the situation is same, that you have to increase the W by L of these MOSFETs. If you increase the W by L, ultimately what will happen? Swing will, your bandwidth will get affected, because your capacitances are increasing, parasitic capacitances are increasing. So this is a very high impedance node. Net capacitance here is, whatever C parasitic comes, that will getting that the R equivalent over here is pretty big. What is R up over here? R up is GMRO square. R down is also same. So basically GMRO square by 2. So net a small signal resistance between this point and AC ground is R GMRO square by 2, which is a large value. As compared to RO, it is having a big multiplication factor. This is a very high impedance node. So if your parasitic capacitance is increased, the circuit will become slow, bandwidth will get limited. So there is a conflict between, of course, the swing and the bandwidth. Is that clear?
Yes, sir.
Okay, so another thing is the input swing. Input swing, in case you are amplifying a very small signal, input swing may not be an important consideration, because here the gain is going to be pretty big, GMRO square, of the order of GMRO whole square, which is pretty big, and therefore the input ultimately what is the input magnitude you can apply is V out peak to peak, whatever you have divided by gain. So V out peak to peak is only this much, right? V out max minus V out min, and divided by the gain when you do. Here we're talking about GMRO square. If I assume GMRO, each of them 50-50, easily the gain is beyond 2500. So even if you say that okay, output swing is somewhere close to say 500 millivolt, suppose, or 0.5 volt. So the GMRO square is going to be much smaller, and therefore, the input allowed swing for that is going to be much smaller. You can't apply a very large signal over here. It has to be very small. So 0.5 millivolt, 0.25 millivolts, lower than 0.25 millivolts. So now here, if you see, therefore we can say that input swing probably is not going to be such a, it has to be small. This amplifier will be used only if your input signal is small, low of the order of 1 millivolt or small. So now, thing is, in certain cases, when we use amplifiers in feedback configuration, like we have seen that we want to use amplifiers in as voltage followers, where output signal is equal to input signal, and we need to handle large swing at the input also. And we want very accurate voltage follower, so that accuracy is very good. We want to maintain good accuracy. At the same time, we want to have large signal swing. So in that case, this kind of amplifier will give challenge, right? So here you can't apply large input signal swing, and you basically also need to maintain accuracy, so you can't sacrifice the gain. So for that purpose, when we use this kind of configuration in differential amplifier, a slightly different topology is also used that you will find in textbook, which is called folded cascode. So folded cascode, the concept is similar. So here, for example, input device remains same, Vn. First, I will give you a simple cascode, and then we have folded. Folded means PMOS is like this. It is called folded because the direction of the small signal current is folded. It is getting folded. And here we put a current source. Suppose for the time being, it is an ideal DC current source, I bias, whatever. Now, V out is being taken over here, V out. This is constant VG2, some M2, and this is M1. In this circuit, what is the small signal gain? Without looking at the, without doing any small signal analysis, what is the small signal gain? How do we calculate? Without doing any small signal, even don't draw the small signal model. What is the gain? Mentally, how do we calculate?
So it would be GMR out. So
GM2
into R.
Sorry, GM?
GM times R load.
GM times R load. Okay. And why it is so? Because here, if you see in the small signal AC model, what will you do? So this is a DC bias current. So what do we do? The DC bias current in a small signal model, we get open circuited because there is no AC current going into the DC bias current. It is always constant. AC point of view, this is open circuited. Open circuit, that means this will be gone. So I can forget about this, right? And now you are left with this one. And this is exactly same as our previous design. Only thing is, the simple cascode amplifier that we discussed is same as that. Only thing is, rather than a NMOS, we have a PMOS. So earlier in the original design, we were having a scenario like this. We are having NMOS input device, and this is the cascode device. This is constant gate voltage. Now, only thing that we have done is we still have the signal flowing into the source of another MOSFET, but it is a PMOS in this case. And then you have RD. So basically, if I see, I have replaced the, I have just made this a PMOS. And then my drain is over here. That is the only thing. Otherwise, circuit, the concept of small signal will remain same. Therefore, the gain in this circuit will remain same. Is that clear? So this followed cascode, how it is working. So why it is called followed cascode? Because whatever small signal current is produced over here, because of the input signal, whatever small signal current is produced, if I assume that this is the ideal current source, this entire small signal current gets folded into this MOSFET. So here it was flowing in the same direction, right? Whatever small signal current is flowing, if it is flowing in this direction, if it is reducing, the whole thing, the whole small current flows in the load also in the same direction. That means VDD to ground. But here it is just the opposite. So here, if it is going downward in this MOSFET, it will be going upward in this MOSFET. So basically, the routing of the small signal current has been folded. That's why it is called folded cascode. Folded cascode. This is important because this kind of configuration is used in differential topology, and that is called folded cascode operational amplifier. So you should be comfortable with this. You should not have any difficulty in understanding how it is working, how the signal is flowing, how the output signal is coming. Those things should be clear. Of course, the bias current over here, you have to set such that, first of all, whatever GM you required, it is coming in the first device. And likewise, in the second device also, you are getting. So the bias current here has to be adjusted properly because the same bias current is getting divided into the two MOSFETs. So here, whatever VGS and W by L you put for the M1, it will determine how much current it is going to take, how much DC bias I1 it is going to take, and the rest will flow into this one. This is clear. This idea of folded cascode is clear. Any question? Now, if I say in this circuit, what is the benefit? If I say in terms of signal swing, is there any benefit? Input signal swing will become more clear. Benefit will become more clear if we look at the stacked load. For the time being, also you can see as compared to this one. Here, if I am talking about the input signal swing, so input signal, if I say that this is the body, or sorry, the gate voltage VB, the bias voltage VB. So here we may be biasing the drain voltage of this one to get the maximum output swing, and then accordingly we also need to see what is the input swing applicable over here. So if I say that my input signal is large and it is going to go significantly higher than the VB, in that case, it is going to significantly higher than the DC potential that you have VG. So you will have a possibility of this lower transistor entering into triode region. So if you want to have large input swing, there also we need to make sure that you have enough room for the lower transistor over here, and the drain voltage does not go drastically down and it does not enter into triode region. So in this case, your VB is not coming into picture. So here you have the DC current source, and it will be ultimately like a PMOS load, right? So if I just draw it in with the full detail, so here it will be ultimately a VG3 PMOS current source, and this is the input device. Sorry, NMOS. This is the input device. V in, and this is your load device. R out. So in this case, my swing, if I talk about it, so here VG2 is coming, and as compared to that, of course, this potential maximum, it can be VG3 plus mod VTP, right? So VG3 plus mod VTP. So the maximum allowed voltage over here, definitely it is higher, and as a result, here you can see for a given input signal, if it is going low, the maximum voltage over here, it can go to a higher value. Lower side, anyway, the lowest allowed voltage will be dependent upon the VG2 over here. So if you keep this voltage too low, if this voltage is going too low, the first transistor, this M1 can enter into triode region. And second is, here also I need to make sure that this transistor is not getting into cutoff. So the lower side, again, the constraint will be coming from the VG2 first, because here you have a higher requirement for the VG2. So you should not be pushing this into the triode region. So swing point of view, we should see that, okay, how things are, how the maximum and minimum allowed voltage levels at the input and output nodes are changing. Now, the benefit will become more clear if I use a stacked version, stacked case. There, let us see what is happening. In stacked case also, we will have similar consideration, input device NMOS, and on the output side we will have the Cascode device. This is still the Cascode device, and then after that we will use two NMOS device as the load. So now we are putting as two NMOS device as the load. So this is your, let us call it whatever, 3, 4. This is your 2. This is your 1. This is your 5. So now this is VG3. This is your VG4, and this is your VG2. Output is being taken over here. V out. So in this case, once again, you can see this is same as our this is same as our earlier Cascode transistor. This one, where you have a Cascode load, Cascode amplifier with Cascode load. And how it is saying, well, ultimately this is acting like a current source. This one has been biased with a constant voltage source. And if I assume that this is acting like a good current source, once again in the small signal analysis, I will for the time being ignore it. Of course, in exact analysis, you don't ignore. Exact analysis, I have to take into account the RO5. So that part for the time being, you keep in mind. But if I assume that this is an ideal current source, I can ignore. And in the if I ignore this, then I have the small signal current, basically whatever is being produced by this one. I had the same logic here. Impedance looking into this, what will be the value? Because now again I have to divide the small signal current. This is the V is applied, the GMVG is being produced, and now the lower branch, of course, you will have the RO of the M1, and I also need to look into the the MOSFET's M2's impedance looking into the source. So this one is anyway same as RO1. What about this one? Looking into the source of M2. It's the same scenario. It is the only thing is it is a PMOS. You are looking into the source of the PMOS, where the drain resistance is what? The drain resistance is nothing else but the resistance of the stacked Cascode MOSFET, which is GMRO square. And therefore, the impedance looking into the source will be divided by the GMRO of the this thing. So therefore, this is again same RO, same concept. Whatever we had applied there, same concept. Only thing is the signal has been folded and we are using a PMOS over here. So the gain, same small signal gain comes over here, same gain comes over here. So the signal operation, small signal operation remains same, small signal gain also remains same. And now if we just put the real transistor over here for the current source, here we can see definitely that the voltages that you can apply over here, the absolute levels of the voltage that you can apply over here. Earlier, the lower level of the voltages, of course, here, if I talk about the lower level, you can go down, right? You can have lower applied voltages over here. If you apply the lower voltage at the gate, what will happen? The current in this branch will reduce, and more current in this branch will flow. And on the upper side, if you are increasing the input voltage, earlier there was a direct conflict between the input swing and output swing. So here, if I increase the input voltage, my output swing consideration has forced me to lower the drain voltage over here, right? So I am trying to push it to lowest possible value so that I can maximize the swing. So if my input signal is increasing or the input signal level, voltage level is increasing, even the mean value of the input signal, the DC value of the input signal, that is increasing, this transistor will enter into triode, because in order to maximize the output swing, I have tried to push this value as low as possible. So I don't have much room to basically have larger input signal or increase the input DC level. But in this case, that is not the scenario. That is, here the output signal is over here, and here this transistor, this particular voltage can be sufficiently high, depending upon what is the VG2. The VG2, because this is going to be VG2 plus VSG, right? So depending upon VG2 and W by L of M2, this voltage can be large. It can be close to VDD, closer to VDD, right? So in that case, I am not basically having a conflict between the output swing and the input swing. I can still have a relatively larger input DC level, or even larger swing. Input signal can go to a larger value also without jeopardizing the saturation region operation of this M1. So that is, this will be useful for our folded Cascode operational amplifier. So the main thing is we are decoupling the swing at the output to some extent from the input swing. So here the output swing, the input level, we can ensure that it can go to higher value based on your, the VG2 and the W by L of M2. This voltage you can increase. Earlier, the drain voltage of M1 was at a very low value to maximize the swing at the output. But in this case, that is not a scenario. So here, this kind of configuration can be useful, especially when we are doing voltage followers, etc. This configuration is more amenable as compared to the normal cascode amplifier. This is clear. So just be aware of this, that okay, means at certain stage we will be looking at operational amplifier built of this kind of structure. So you should be able to correlate that okay, this is nothing else but our normal cascode amplifier concept that we have discussed. Only thing is the signal has been folded into the opposite branch using a PMOS cascode device, and then the load has been replaced by a NMOS cascode. Earlier it was a PMOS cascode load, now it is an NMOS cascode load. Is that clear? So all the sizing consideration for this particular thing we'll discuss when we look at the actual differential version, where we are looking at we are trying to have a operational amplifier. So this stage itself it provides a basically single stage operational amplifier. That means within a single stage we are able to get a huge gain. So we don't even need multiple stages to get a large open loop gain. So this amplifier has some benefits, and when we use it as a differential operational amplifier, there it has basically simpler frequency response, because you can see that the main benefit of this one will be that the dominant pole is coming at the output, and it is pretty big because the RC time constant over here is pretty big. The RO is pretty large. So because of that, the dominant pole becomes very clearly distinguishable. That is at a much lower frequency. So that is helpful in stability. It is helpful in making sure that the feedback basically remains stable. So those things will become more clear when we look at the differential operation and also the feedback operation. So for the time being, just assimilate this, that this is a topology which is useful, and whatever analysis we are doing, whatever understanding for the small signal analysis that we are doing will be useful when we study the differential version. Is that clear? Any questions in this behavior of this circuit, like what small signal concepts, anything which is not clear? Remember that we have taken an approximation that okay, this is a high impedance current source is ideal and everything flows into it. If the current source is not ideal, all you need to do is what will happen if your current source is not ideal? If I have this kind of simple current source, what will happen? So only thing is, earlier I was having division between RO1 and this, looking into this side also it was RO. Now I will have another RO, right? Because looking upward, this current source will also provide RO. Now we have at this node, so I have a small signal current. It is getting divided into 3 ROs: RO of this MOSFET, RO of the other branch, and RO provided by the current source. Then basically it will get another, by 3 factor rather than by 2 factor. That's the only thing. But that is not a big disadvantage because the gain is GMRO, whole square, or the order of GMRO whole square. So that is not a big problem. Is that clear? Any question before we proceed further? Biasing, etc. also we will look at later, because right now anyway the output here also the same problem. You can't have a stable output biasing. So this biasing will be done for the differential mode. Conceptually, you should understand what is the small signal current and how it is leading to the gain overall. So before we go further, the same concept, since we have covered cascode, so we can also cover the current mirror based on this concept, which is also very, very important, just to complete the picture, because ultimately the same concept will, same cascode load, cascode transistors will come into picture. So current mirror, you are aware of this simple current mirror, right? So what is it? So this is, we can put whatever load we want over here. It's for the time being, I'm just putting a resistive load. So this is my, I want to generate a current I out. This is DC current. This is my load RL. It can be anything else. It can be a transistor. It can be some circuit. Where did it go? Yeah. So I am using this current mirror. Suppose for the time being W by L is 1, 1. So both of them are same. So what is the problem here? Why are we? Is there any problem? Is it going to work?
So the node is floating, the gates, they're floating.
Okay, so what about this? Yes. Yes, hello? Am I audible?
Yes, sir, the screen was stuck for a bit.
Yeah, so what about this? This gate is not floating, so this is going to work.
The impedance would reduce too much. Should be higher.
Sorry?
For an ideal current source, the impedance would have to be higher. They have to,
Yeah,
increase
the output
in
impedance has to be higher. So if you direct connect it, then we know that the impedance looking into this node is 1 upon GM of this MOSFET. The moment you have direct connected MOSFET, you should, this also you should remember, there's nothing to be forgotten. They're very, simple thing. Impedance looking into this drain will be 1 upon GM, whether it is PMOS or NMOS. The drain gate, the moment you're connecting it, the impedance looking into the drain will be 1 upon GM. So that is one point that, okay, we want higher output impedance. But suppose we are, the RL is close to 0. I don't want output impedance, but still, is it going to work as a current source? Like, what is it functionally correct? We want IREF, right? So I want I out equal to IREF. So is it going to work? Is it going to mirror IREF?
So the like on the left transistor, we have like the gate connected to the output where we're applying the voltage. So just to be
So what?
So it'll try to follow like the VCC divided by RL. It'll treat that as a current source instead of taking IREF.
No,
It will
VCC
try.
divided by RL, you are saying from BGT point of view. So here, so you are partially correct. So ultimately, in this case, the current in the branch over here will be determined by RL, because here you have the VGS, which is the gate drain is shorted anyway. This is in saturation, and the VGS is going to be determined by whatever current is flowing from here. So simultaneous equation, VDD minus whatever is the VD upon RD. This should be equal to what upon mu n ux W by L, whatever. VGS in this case is same, VD minus VT square. So this is the equation it will follow, and it will give you the VD. So simultaneously you can solve these two parts and quadratic equation, and you get the value of VD, which is also going to give you the value of ID, whatever is the ID. So this itself is a reference. So this simple branch can be used as a reference, in fact, which is not a good reference, but in simple design you can use this as a reference. So to generate a required amount of current. So here it is not going to mirror this. What is happening to this? Why? So here, why it is not able to mirror? First of all, because the gate over here, it is not being determined by this IREF, right? So if unless we ensure that the gate voltage over here is determined by this IREF, we will not have I out equal to IREF. So here the gate voltage is determined by the RL, whatever is the RL, and depending upon the the current solution that you get for a given RL, whatever is the voltage drop that you are able to support at the gate, and for that gate voltage, what is the current coming? That is determining the gate voltage. It has no relation with the IREF. And why there is no relation? Because here for this MOSFET, if you put a, say, suppose it's an ideal current source. So for an ideal current source, whatever you do, whatever happened to this MOSFET, this current will remain same. It will always provide this IREF. Now, if this always provides the IREF, then what is happening? So here you have the gate voltage VG will be determined by this equation, which will come, the VG is equal to VD. So it will come by this equation. And now I have another variable for this MOSFET, which is the VD. So now the VG is forced by the RL. For that VG, whatever is the VD required, it will get established because you have forced the IREF. So this MOSFET, you have forced the IREF. And therefore, the drain voltage over here will be dictated by IREF. It will still support IREF for this given VG, but this VG is not determined by RF. This VG is determined by the RL on this other side. And for this given VG, the drain voltage over here will be determined by whatever IRF you put. And as we know, this is like a common source amplifier with active load. This node voltage will be a very high impedance node because this is R up parallel R down is RO. Therefore, this DC voltage is very non-deterministic. It can go very high, it can go very low, depending upon the value of the RO and the ID. This is not a well biased node. So the reason we connect the diode for the reference branch, if you are having this as the reference branch which you want to copy in the mirror. So first of all, let me write it properly. It is not looking like reference IREF. So if you want to copy this, first of all, I need to make sure that the gate voltage of this branch is getting determined by IREF. So this IREF should determine what is the VG1. And then in this case, of course, there is, the IREF alone is determining what is VGS. So for this gate voltage, the only thing I need to solve is this equation. This should be equal to IREF. And therefore, VG is solely determined by IREF. Now, once you have, of course, lambda, you can ignore for the time being, as we know that, you are setting the VG and the VGDs shorted, and the VGS has a much stronger dependence. VDS is same as VG. So for a given same VGS VDS value, the VGS has a stronger dependence. So I can ignore channel modulation, and I can say that okay, I can solve this quadratic equation, find out VG. Now, once this VG1 is developed out of IREF, then I can apply the same VG to the other device. And if the VGS of this device is getting fixed, which is again derived by IREF from derived from RF, now it will basically produce the same IREF provided the transistors are identical, and then you can connect whatever box, whatever circuit you want to keep here. This you can keep, provided this voltage is not bringing M2 out of saturation. So the condition will be that V out over here, V out DC should be greater than VG1 minus VT. Assume that VT of both are same. So as long as this M2 remains in saturation and V out over here remains higher than VDG1 minus VT, it is going to follow. It is going to act like a good current mirror. And then you know that okay, if you want to change the W by L, if you want to mirror, you can increase the W by L of 2, and by changing the ratio, VGS remaining same, you will get almost that amount of mirroring. And looking at the non-ideal behavior, of course, lambda is there. And if this V out is not exactly same as the other one, you will get some lambda dependency, definitely. So if your V out is increasing here significantly, then the current over here will also increase. It will not be exactly same. It will increase as the V out increases. Likewise, if the V out goes down as compared to this one, the current will start reduce, right? So and finally it will enter into triode region. So those things you should be able to visualize, that if your V out is going too high, how the current in the output branch will increase, and if it is going too low, how the current will decrease, and finally M2 entering into triode. So here the question is, the issue is that still we do not have basically we do not have a very good output impedance. We have still RO, just RO, and we have seen just now that okay, we have a good way of basically generating a good output impedance. So if I stack another transistor, we can get GM-RO square, right? So that is what we have discussed. So now I can definitely do this in the reference branch, whatever current is coming, and I can stack another transistor, get a VB over here, and then I can take my output current from here, I out. In this case, my output impedance is GM-RO square, right? Because looking into the drain of a stacked MOSFET, if you have two MOSFETs like this, you get GM-RO square. So as compared to RO, the output impedance is boosted by GM-RO, which is going to be a large number. Output impedance is going to be larger. This is going to act more like an ideal current source. The ideality has increased, or basically the ideal behavior is increased, or it is coming closer to an ideal current source because output impedance has increased. Now the question is, how do we generate the body voltage over here? The gate voltage over here. So one way to do it is to just add another diode connected MOSFET on the top of the other one in the reference branch. If you do this, then of course we have basically the voltage VG2, VG1. Both of them are getting established by the IREF. So here both VG2 and VG1 are determined by IREF and W by L of these transistors. So once you know what is IREF, once you know what is the W by L of these transistors, you know what is the VG1 and VG2. And the same is being applied to the same VG is being applied to the other transistors, and VGS of these transistors, expectedly they are same. At least for the bottom transistor, definitely you can see that they are exactly same. Therefore, it will establish the same current. And then you have basically the same VG of the second MOSFET also. Now the current forced by this bottom MOSFET is also similar. So whatever IREF you are flowing and you are establishing same VGS, so it will also try to establish same IREF, because for the bottom MOSFET IREF current is being established by VGS, and therefore same current flows through this one. And if the VG of these two MOSFETs are same, it will also try to establish almost same voltage at this one. So this potential will also be coming close to VG1, which is the drain voltage of the other transistors also. So this is a cascode current mirror. Cascode current mirror. And the benefit is that the output you have a higher impedance. But then if you talk about the swing, then another issue that in current mirror that we have is the signal swing. So if I want to find out what is the maximum signal swing at the output, what is the equation for this case? What will it be determined by? Yes, quickly. So this is your again IREF, and you're talking about the V out over here, and then I want to find out what is V out. See, V out max, there is no problem, because V out max, if you go higher, only thing is it will be constrained by the upper circuit, whatever you have. So what we are concerned with is the V out min. What is the V out min? Because if you lower the V out min, then the current source will be in trouble, because we know that in this case, if this is VG2, this is VG1, V out min is what? V out min is VG2 minus VT. So if you lower the V out min, this current mirror will not operate properly, the current source will fail, and therefore you will not get a good current source for your circuit. So we are concerned with V out min. Now, in order to make it a good current source, I would like to minimize V out min. I would like to keep the value as low as possible, or allow lowest possible V out min. That means I can handle even lower voltages. So for that, first of all, we need to find out in this circuit what is the V out min. So this is VG1, right? So VG1 or VGS1. I can we have seen that VGS I can write down as V over drive 1 plus VT1. So V over drive is VGS minus VT. V over drive definition is VGS minus VT, because that is what determines the current as compared to VT, how much you are overdriving the MOSFET. That is V over drive. That is VGS minus VT. So VGS1 is V over drive 1 plus VT1. And therefore, what is VG2? That is again VGS1 plus VGS2, right? So VG2 is nothing else but VGS1, this voltage VGS1 plus another VGS2. So plus VGS2. So what is it actually? So if I assume that MOSFETs are identical, it will give you 2V over drive plus 2VT. This is clear. And therefore, what is the V out mean? V out mean according to this equation will be what? V of VG2 minus VT. So we will get 2V over drive plus VT. Now here we are getting 2V over drive plus VT. So here now if you want to minimize it further, that okay, you want to go down. What is the way how to do it?
Increase W by L of all the transistors.
So if you increase W by L, the V over drive will become smaller and smaller as compared to VT. And therefore you can say that okay, as compared to VT, I will ignore it and it will become almost close to VT. So VT, suppose in 180 nanometer you have 0.45 or 0.5. Generally it's 0.45 for nominal, I think, for 180. And V over drive, you are reducing it so much that it is becoming just 50 millivolt. So T over drive will be just maybe 0.1 volt. As compared to VT, you are reducing it significantly, and therefore you will be limited mostly by the VT of the transistor. So you can say that okay, in this case, 2V over drive plus VT, and this VT term is going to basically this is called headroom. It is taking this is called headroom, right? So when you try to stand tall, and if your ceiling height is small, you will have to bend down. You can't, you don't have enough headroom to stand or raise your head. So likewise here, this voltage doesn't have enough headroom on the lower side. So now at least it has to have a VT. So at least it is consuming, basically we say that it is needing a VT plus 2V over drive headroom. Without that, it will not operate. That is the constraint. In the simple current source, what was happening? Simple current source, so what was the output? mean output mean was simply VG minus VT, right? So in this simple one, this is VGS and this is VGS minus VT, VGS minus VT, which is basically just V overdrive. And this V overdrive I can further reduce by increasing W by L. Again, increasing W by L, you can't blindly go on increasing W by L. It has its own issues that we'll discuss. Will we discuss the differential amplifier case? But V overdrive does have basically at least we can reduce. So in this case, you can see that definitely you are adding a VT. So you are eating up some headroom, or basically you are demanding more headroom for the current source to operate, which is kind of a disadvantage. So in order to mitigate the disadvantage, we have a slightly modified configuration which people use wherever there is a constraint, wherever there is a need for higher headroom. We have a modified version, and that modified version you can quickly understand. These things will also be commonly used. So you have to be aware of these. These are common blocks which are used everywhere. So you should be getting familiar with this. Now this thing, if you see, yeah. So now the strategy over there is that okay, now you have a current source, and now you put a resistor over here, and the bias, the connection goes like this. So the gate of this one is connected to the lower end of resistor, and this is the current source. The only thing is drawing sometimes gets messed up, so let me draw the current source properly. This is current source coming from VDD, whatever. So this is your I ref, whatever you want. And IREF, we have not discussed how to generate IREF. One of the simplest thing that we have seen is okay, you just put a resistor and a MOSFET that generates IREF. But we will discuss more accurate methods, and the reference generation itself. I think rather we also have a dedicated chapter just on reference generation. You can look at it. Now, if this is your R, whatever R naught, and now the gate of this one will be connected to this one. So look at the connection. The gate of the lower transistor connected to the drain of the upper transistor. Gate of the upper transistor connected to the upper end of the resistor, and then you have the output. Now, if you see this voltage is what VGS of M1, right? So VGS I can again write as V overdrive plus VT. Now I have the option of now what is the I can choose this gate voltage such that the required gate voltage I can choose to minimize whatever is the I want to minimize this gate voltage ultimately. So that will depend upon what is the minimum voltage possible here. So what is the minimum voltage possible here? V overdrive plus VT, VG. This is the VG for this. The minimum voltage possible here is V overdrive plus VT minus VT. So this will be V overdrive minimum allowed. Now, as compared to the suppose we are trying to push it to this one. So as compared to this one, what is the voltage here? This will now be. This is our VS. So this VGS is nothing else but again V overdrive plus VT. So this will become 2V overdrive, right? 2V overdrive plus VT. Now this gate voltage is 2V overdrive plus VT, and therefore the minimum voltage that you can have over here is what? 2V overdrive. So now to this takes us to the similar similar values to the earlier case. Now this V2 overdrive I can minimize by the sizing up so that my headroom that was consumed by this VT is gone. And now you just have to take care that okay, what is the voltage drop across this resistor that you are getting? At this node you have basically 2V overdrive plus VT, and this node you have V overdrive plus VT. So overall you are getting a V overdrive drop across the resistor. So you have to size the resistor such that the V overdrive across V overdrive upon RD is equal to IREF, and you can based on that you can size the W by L of this MOSFET. Also you can try to increase the W by L so that you get a proper lower V overdrive, and you check the RD accordingly, and that basically helps you in getting a reduced headroom at the output. This is called reduced swing cascode current source. Reduced swing is not a very good nomenclature. You can say basically, yeah. So actually, the swing is improving. Generally, in literature, you will see they call it reduced swing cascode. But the actual thing is that your overall output swing or the minimum output value that is applicable is improving, because you can now go to all the way to 2V overdrive, which can be much lower than 2V overdrive plus VT. Is that clear to all of you? So this is a good current source and commonly used. We will discuss some other configurations also which are even better. For the time being, this is pretty standard. And whenever you need a very good current source, very high impedance, and it has its effect, a good current source also is very important for differential circuits. Those things we will study a little later. But both simple as well as cascode current source you should be comfortable with. Another thing that you should also comfortable with is the current steering circuits, which are also very commonly used in biasing, multi-stage amplifiers, etc. Current steering means you are basically. Hello, am I connected?
Yes, sir.
Hello.
Yes, sir.
So current steering means you are basically changing the direction of the current from PMOS to NMOS, and then you are routing it back into another branch. So, for example, this is an example of current steering, where you are whatever. So here you are having RD, and you are getting IRF over here, and then maybe you are having W by L, you are having 4W by L, and then this is also whatever W by L2, and this is whatever 4W by L2. So whatever current is produced here, reference current, it produces the VGS required for this MOSFET M1, and that same VGS is over here. So this is the first current mirror, and this current mirror is producing 4 times IRF over here, because these two are having ratio 4 times. So whatever IRF produced over here, same VGS for these two MOSFETs, M2 and M1. Therefore, W by L is 4 times. It will get 4 times IRF over here. And now, of course, channel length modulation, if it is very serious, it may be slightly different. It may not be exactly 4, but close to that. And then now you are having another mirroring stage. So now you are basically taking this 4 IRF, and again 4 times over here, you are going to get 4 times 16 IRF over here. So basically, uh, current steering means ultimately you are folding the direction of the current. Here, this is sinking the current, and then this source is supplying the current. So in many circuits, you will need bias for both sinking as well as supplying. So if, for example, if you are having a say we have seen the cascode current source, right? So cascode current source we saw, sorry, cascode current mirror. Again, I'm using a long term. So cascode amplifier. So we have seen the folded cascode amplifier. So there, what did we see? On the top, we had put a current source. That is the PMOS current source, right? So this is the input device, and PMOS current source. Now this has to be biased using something like this. If you go for the other case where you are having the just the opposite, there the current source is NMOS, then you will bias it using this particular one. So in many cases it will be required that these currents are exactly same, or basically very matched currents. So this current, whatever current we are supplying to this stage, is also very it is very close or very well matched to the current which is coming in some other branch. So from the same reference current, many times we will need to generate sinking source as well as sourcing current source, sinking current source. So this NMOS is a sinking current source because it is sinking the current, and the PMOS is a supplying current source or sourcing current source because it is sourcing the current. So that just terminology you should keep in mind. And using the same reference current, you can do this by this kind of current steering. You can generate both the sourcing as well as sinking. Is this clear? This is very simple. I don't think there is much to be discussed. Any question? Okay. So before we conclude, just one discussion that I wanted to have that may be useful for your assignment. Assignment, I'm waiting for it because I wanted to complete certain things and then only give the assignment. But today again, I did not. Today my agenda was to complete common gate and common drain also, so that I could give you something. But that has not been completed. But still I will give you something, some nice, small part, initial part, so that you can still start at least, because it has been long time since I gave you assignment. So we discussed this thing, diode connected load. Now, if you have a diode connected load like this, and if I have to make another stage, I want 2 stages. So is this going to be okay? Like, if I do this is okay. This is your first stage M1, and what I have done is just output of the first stage. This is the output of the first stage VO1. I have connected to the input of the second stage, and now I'm going to take VO2. This is okay. This is fine. Is there any problem that you see? Just two-stage amplifier. So just using the diode connected MOSFET, I have created two-stage amplifiers. Both of them are diode connected. Is there any problem? Quickly, time is going. We are running out of time. Are you seeing any problem, or is it perfectly okay? It will work. I'm not saying it will not work, but there is a issue. What is the issue? Hello, am I connected?
Yes, sir. Stage. By excellent. By so like, so this is the first stage is like going to have a negative gain, right?
Yes.
Okay. Then we are giving that to M2. So maybe the DC bias may not be matched properly. So the second stage may not be.
So why it is not matched properly? What do you mean by DC bias not matched?
So M2 might be off, like it may not be like VGS2 lesser than VTN.
Why? I was very happy when you said the first part of the answer. Second part you messed it up. Second part, what you said is just the opposite of what is actually happening. So look at it carefully. What is happening? So apply some values. So I have given you some values of 180 nanometer. That okay, this is the VT 0.4, VDD 1.8, and then think about what are the values you are getting at the different. So calculate. Just assume. We have already given some example, right? That okay, VDD, VT, V overdrive. What are the nominal values you can assume, and then try to figure out what is happening. Okay, so let's so the answer is partially correct, as I said, which is good. At least we have tried to identify that is the issue. So this is 1.8, 1.8, and suppose VT is 0.4, and here the VDD is this VSG is 0.5. So you are getting this value is 1.3. This one again VGS you have kept is 0.5. V overdrive is 0.1. What is happening to M2? M2 is getting a huge V overdrive, 1.3 minus 0.4, right? So what is expected? So this transistor will end up burning huge amount of current here. And second thing is it can enter into the triode region very fast because the gate voltage is high, 1.3. Moment, here at this point, what is happening? 1 point is just 0.5. Output voltage can go down all the way to 0.1, but here it is 1.3. And the minimum value that you can have over here is in this case only 0.9. That is one thing. Output swing is getting reduced. Second thing is this bias current is going to be huge. Means as compared to 0.1 overdrive, here you are providing a huge overdrive. So that will basically unnecessarily waste a lot of current in this stage. That current is not desirable. Why it is happening? Because this, whatever VGS 0.1 overdrive you provided for the NMOS over here, that created a corresponding V overdrive for the PMOS. Now this gate voltage is suitable for biasing another PMOS stage, but you are applying it to the NMOS, and that is producing a huge V overdrive, right? So this 1.3, if you apply it to another PMOS stage, like if I apply it to this next stage, if I make like this, sorry.
So then that PMOS also has 0.1 volts overdrive because we want those.
If I do this, then then it is safer. because now this is matched. This is PMOS, and this is 1.8, and this is also getting almost similar VSG. So DC point of view, this is much more safer because the DC bias gate voltages are well established. But in this case, you are forcing a much larger viewer drive on NMOS, and that will basically first of all burn huge current in this MOSFET, and there is a high possibility of M2 entering into triode, and the gain will be messed up. Output DC bias point will be messed up. So this is not a good strategy when you are in this kind of configuration. Here you have to make sure that when you are cascading amplifier, what are the DC level provided by the output of the first amplifier, and you are connecting it directly to the input of the next amplifier. So the DC levels should be commensurate, should be matching. It should be suitable for the next stage. So here you are not considering that. Whatever DC level you are getting from the first stage are blindly connecting to the next stage, which is not going to work in this scenario. Whereas this one, it is going to be okay. So I hope this one also. So this will be this will be useful again when we are looking at multi-stage amplifier, differential amplifier, etc. And this also this came to my mind because this is also linked to the current routing scheme that we are looking at. So as I said here also, in many cases, some circuits will be requiring the biasing for NMOS tail current source, and some other connected circuits will require biasing for the PMOS current source. So depending upon which circuit, what is the whether we are working with NMOS input device or PMOS input device, we may have to establish the right kind of bias currents using this kind of current steering. So I'm just giving you the building blocks for differential discussion. So right now, all these concepts that we are discussing here, they are forming the building block for your discussion on differential amplifier, operational amplifiers, which are ultimately going to help you in working on, real project problems. This is clear. Any question on this before we conclude? Already I've taken a lot of time. Any question before we conclude? Okay, so I think let us, if you don't have any question, let us, conclude. And I hope things are clear. Are you able to? I mean, everything is understandable or any problem? So I hope I'm not going too fast. Is it okay? Anybody else would like to speak? Whether it is too fast, or whether it is okay, whether it is slow. Yes. Any comments?
Yes, it seems okay to me.
Yes, sir, it is fine.
Yeah, it's fine. Speed is fine.
Okay, so this is good. I have to actually, whatever whatever I'm planning, I'm covering much less than that. So today I was supposed to finish off common gate, common drain, but that did not happen. So that I have to do maybe tomorrow. And I don't have the recorded version of these, so I can't give you recording also. But anyway, so I hope this is clear. And then let me think of some good small example, the assignment that you can all do. I will explain it and I will post it in the group so that you can take it up. And before tomorrow's class, you can do something, because it is important that whatever you are studying, you are also simulating and understanding it. If you don't do it for single-ended version, directly jump on the differential version, you will not be able to appreciate. So it will be better that single-ended version also you do some good analysis, and then you come to the differential version. Many things can be done using single-ended. It's not that single-ended is not used. Single-ended is also used. For example, interestingly, just now we are working on some project where uh, there are single-ended as well as differential versions of a circuit. Single-ended is having more challenges because of all the noise, etc. And we have to deal with it because it's required. In certain applications, single-ended is required, so we have to deal with it. So it's not that single-ended is not used absolutely. Many cases it is used and it has its own challenges. So I'll give you some small analysis for the single-ended also. I was just waiting for the common gate and the common drain to be over so that you can work on a multi-stage thing. But you can still probably here also you can do it. At least some part you can start with. Ajay, tell me what is the, if I give you this amplifier, what is the gain of this amplifier? If I give you amplifier like this, V in V out, and this is R. and this is your VDD and ground. So what is how will you find out the gain? Suppose I simplify your life. I say that R tends to infinity. Then what is the gain?
R is infinity, then like can we number them? Like, so if this one is M1, that one is M2. Like lower one we can call M1. Okay. So minus GM1 plus GM2 into R01 parallel R02.
Yeah, because you can take superposition, right? So you can divide it. You can say that okay, I will take V in. Both of them are having, both the gates are having V in. If I consider the gate input of the first transistor, that is M1, I can assume superposition and other signal. I can put it to 0. So in that case, it simply becomes AC ground, and it becomes a common source amplifier with input at the gate of M1 V in. And other case vice versa, it will become like PMOS having input and the NMOS AC ground. And both the cases, the gain from the input output is same. So it is inverting. Here also from PMOS side also you will get the same inversion, and NMOS side also you will get the same inversion, and the magnitude is still, so I can simply add. So V out will be simply GM1 plus GM2 times RO parallel RO2. Is it clear to all of you? If you other extreme, if you take RO equal to 0, definitely we understand that V out equal to V in. If RO is 0, it means shorted, and then these two are not performing any job in amplification. V out is equal to V in. So now if I give you R equal to some intermediate value, and then try to say that okay, what is the gain? So you can do the small signal analysis and find out. And the other thing is, why I'm giving this is because it has some nice concepts, and you can get some insights. So now if you for example, why are we using what is the benefit of using R at all? Like why we at all insert R?
I think there's some feedback happening when you get a stable gain. Like here we have
A stable
GM1.
gain. Yeah. Fine. So stable gain, and also another thing, what is it? Gain is fine. You are getting a feedback, and that will help you in getting. But apart from that, any other point? Can I use this inverter directly as an amplifier? Directly, this one is we have seen, right? This is also we can use this as an amplifier. So what is the problem? Why are yes? What is the problem? I can apply a small signal model. I can get a small signal at the input. I can get an amplified output. We know that there is a gain. This is if I apply the if I use this slope region, I can get a good gain, maybe. Especially if you use larger channel length for this one, if your GM as well as RO is good, the gain can be pretty good. So what is the problem? Quickly. Yes. Quickly now. By now you should be able to answer this. What is happening?
So
Yes. Sorry. What is the problem? What kind of load it is?
uh, So much we have discussed, and still you are not able to answer this. So you should, even after the class, you should look at the lectures, take the snapshots if required, make a PPT out of it. So so that you remember the concept. It is important to revise. If you don't revise, things will not come. This is very simple. So answer is probably not clicking why I am asking this question, but the concept is very simple. So, so I said that single-ended common source amplifier cannot be used easily, but this one can be used. Why?
This one means this one, the one with R. It can be used. This cannot be used. Yes, tell me.
So like is there some common mode signal like between, is there some
What
noise?
common mode? The common mode and differential comes when you have a differential signal. This is all single-ended.
Like so between no, but that not okay, no.
If you look at the transfer function and tell me something, are you getting any clues from there? I hear only two Y's. One is I think Ariman, and another one is I think nobody else speaks. Another one is as far as I understand, sometimes Macha Vashishta is speaking. Sometimes these are the two people, Ariman and Vashisht. Maybe Alka Prava sometimes.
So like the
What about
output
other people? Other
impedance,
people? Yes, who is speaking? Yes.
so the
Let
output
me see.
resistance in case of the inverter is like ROP parallel RON, so that is large. So
Oh,
bandwidth limitation, maybe.
no. I will give you all the hint. Look at the transfer function I told you. Of
Oh, so it doesn't go to like exact zero, maybe.
in order to get good gains, you need to make sure that V out equal to V in curve is over here and it is basically cutting this in the center region. I need to bias it, right? So here, this is not a bias. Output point cannot be biased. I told you the common source amplifier cannot be used with active load directly single-ended. You can't use it because of bias. Output DC point is not fixed. The moment you do this with a large R, you are forcing the DC at the input and output to be same. And if that is same, V out equal to V in at DC, that means you are automatically bringing it to the high value, is high gain point. And therefore, after that, you can apply a small signal and get a good gain. Is that clear?
So how
You can
like
also
large resistance we keep the DC value same, like how does that, like how do we like calculate that?
how do we calculate that means what? So in the transfer characteristics, if you have two curves, V out equal to V in and this transfer characteristics, the intersection will be the point where the DC value will lie. Because by forcing this, you are making, if I assume that input basically impedance is also very high, or you can have a capacitive input, capacitively coupled input. Suppose this is the input stage, and the input is coming from a sensor, capacitively coupled to this stage, and then there is you can say that the input is not drawing any current directly, it is not drawing any DC current. So if I analyze this circuit in isolation, because there is no gate current in the MOSFET, right? The DC current in the gate is 0. So that means the out and the in voltage must be equal. So it will settle at the point where V out equal to V in, right?
But so like that may not be the case for maximum, like we have also the condition for maximum symmetric swing, right? For V
That
out.
will also be if you look at this, it will be almost giving you the condition or basically giving you good swing also because it is midway. So V out equal to V in is generally in this transfer characteristic is exactly close to the midway. If you transistor size, so that that is also determined by the PMOS and MOS ratio. So PMOS and MOS ratio, if you just adjust the ratio properly, you can make sure that it is exactly midway. So that is not a problem. Okay, so so right now I think I will. Right now it will take time if I start describing the assignment. I will record it and I will give it to you. It may include this stage also, and then you will have to look into it. Is that clear? Any question? This one you will get an assignment. So just think about it, and it's a very simple circuit. But if you simulate, you will get to see, and also the small signal analysis you can do and find out what should be the gain, what should be the impedance, and you will have to see how it is coming in the actual simulation. So, and after that, I will give you some. This will be followed by some other stage also. So I will give you assignment based on this for tomorrow. So simulating single-ended is also going to be very important because ultimately, if you don't understand, if you don't get a taste of simulation single-ended, you will not get it. You will not appreciate the differential directly. So before you get into differential circuits and operation amplifier, more complicated circuits, at least some simple simulations you should do for single-ended. Is that clear? Any question before we conclude for today? Already I have taken 1.5, so it's already a lot of time. Yes. Any question before we conclude? Okay. If you don't have any question, let us conclude and wait for the assignment. I will post it by tonight. Then you will have at least tomorrow full day before the class. Okay. Thank you.